So thank you very much for the good introduction, and thank you all for being here and attending my speech on the automated retrieval of similar CAD-parts based on dimensionless invariants. And as you already said, something about the company. We're working on different fields, mostly design automation, graph-based design languages, and also automatic wiring, which you can see down here and which we'll also see on the next slide, because our problem context is based on this example. And the situation is that we have, for example, an automotive company which produces this cockpit and then gives it to another company which shall produce the wire harness for this cockpit. And when this company has finished the work, they have lots of cables and lots of connectors, and the big problem for them is they use their own part numbers. So they have connector ABC, and the car company that wants their own part numbers. So let's say they want BMW 123 and not supplier ABC. And this is a big problem because it's not that they just use 20 different connectors, because then it would be very easy to just sort this by hand. But the problem is that there are a lot bigger numbers of connectors because there are several thousands. So, and this leads to the problem formulation. Let's say we have one connector and we have a large database. I can just show 48 that we used for our study because 40,000 wouldn't fit on the slide. And here we want to know which connector down here is the most similar or even identical connector to the one we are regarding right now. And as you can maybe think, the answer to this question depends on the definition we have of similarity. And therefore I would like to take a short look at some definitions of similarity on the next slide. And here we have two similarity definitions. The first one is very commonly used in artificial intelligence, where we have an object, then a kind of image representation. We therefore use human constructed feature extraction and have a data-driven classifier, which is often used in neural networks, but is not limited to this application field. And what we want to focus on more is the similarity definition in physics. So we use physics-based features and distance metric as classification. And maybe some of you also know this as the pi theorem. And the important part here is that we have dimensionless invariants, which will be explained further on the next slide. And then also there is the possibility to go back this way, which means that we do not lose information when we do our classification. And this is based on some previous work in our research group. So, as you have already seen on the slide before, similarity in physics is based on the pi theorem by Buckingham, which is already a little bit more than 100 years old. And a little bit small everything on the slides, I hope you can read it a bit. It basically says that if you have a dimensionlessly homogeneous function, small f, which is dependent on the values small x1 to xn, so we have n of variables that is dependent on. Then there also exists a dimensionless function, which is written with big F, which is dependent on pi 1 to pi m. And this is not the same number of variables that it's dependent on, because we have a reduction of variables, which result from this so-called dimensional matrix. And yeah, if we write all variables x in a matrix, and then we get the rank of this matrix, then we also have the number of dimensionless products, because the number of dimensionless products is the number of the original variables n minus the rank of this dimensional matrix. And what this means, that we have this dimensionless product, and if all dimensionless products of two regarded objects are have a constant value, this means that they are completely similar. And this implies that different values in x can fall on the same values in pi, and which means that different things in x can be identical in pi. And since the pi theorem enables us to compute dimensional similarity numbers from dimensional variables, the key question is, how can we transform geometry into a dimensional representation so that we can also get dimensionless invariants from geometry. And this I will try to explain on the next slides. And we also use some kind of image transformation, but you don't have to think of it as image like a picture, but more like geometry in this case. We have this equation in which we have an integral transformation from the original geometry, which is described with the function small f, and this is mapped to the so-called central moments. And there we have the three directions, x, y, and z, and a function that describes the shape. And if we simplify that, we don't use the infinite bounds, but just the space that the part is occupying, and therefore we don't need a function that describes the part anymore, because this is 1 when we're inside the part and 0 outside of the part. And with this simplified formula we can then do numerical integration to get the values for the central moments of geometric shapes. And after we calculated these central moments, we use 3 of them, the 200 and the other 2, and then we can normalize the other values to have dimensionless invariants. And in this case, this is again based on the dimensional matrix, which I explained on the slide of the pi theorem. And in this case, the length information is divided in length in x direction, length in y direction, and length in z direction, which is just used to increase the rank of this dimensional matrix. And with that, the process chain is completed. We start with a geometry in, for example, step file format, could also be some other format. We just need to mesh it so that we get tetrahedrals, because we need them for the numerical integration. And with these we can calculate the central moments as explained before, and after that we can calculate the dimensionless invariants, and so we get a feature vector of dimensionless invariants for each geometric object that we regard, and this makes it easy to just do distance calculation between these feature vectors. For example, Euclidean distance, or also other distance measures are possible. And as you have already seen on the slides before, we used connectors as example. These are 48, which will be shown on the next slide a little bit bigger so that also the people in the back can really see them. And what you may notice when you see these images, that a lot of them already look similar in the way we normally use this term, because they are from same manufacturer and are some kind of series where they just have a varying number of electrical pins. And what we hope for, that this would also reflect in our research when we further use this for analyze these connectors. And to show our analysis, we have a big distance map, which I will explain with this small example, because then it's a bit easier. This diagram has to be read row-wise. It, for example, says that to the connector 1, the most similar is connector 2, and the second most similar is number 4, and third most similar is number 5. But the important thing here is that it's not always the other way around. It's not a necessity that it's also the other way around. Because if you look at connector number 2, the most similar in this case is number 3. So even though it said connector 2, the most similar is, number 1 said most similar is 2. 2 doesn't say it's 1, but it says that number 3 is the most similar to this connector. And with this explanation, I can show you the full distance map. And yeah, I hope you can see it good enough. And the main diagonal is grayed out in this case, because this will only tell us that the most similar connector to number 10 is number 10, and this is not a helpful statement in this case. And what we can already see that most of these similarity are along this main diagonal, and this is the case because we already sorted them on the visual appearance and hoped that this will show in the distance map. And what you can also see here with these blue squares is some kind of similarity grouping, because in all of these blue squares, the references to the most similar, second most similar, and third most similar connector are all pointing to another connector inside the square, so we have some closed groups. And these were the ones we hoped for, because these are the series of connectors which just have a varying number of electrical pins. And to better explain these groups, I will go through 4 of them on the next slides. So this is the first group. Again, we have the same colors. The red arrows mark the most similar connector, which in this case is not always the one which has 1 pin more, except for the last one, because there is no bigger one, then it also points backwards. And what's also apparent here, that the second most similar and third most similar are, a lot of them are pointing to a middle-sized one, because smaller and also bigger connectors can reference to this middle-sized one. And when we take a look at the next group, we have exactly the same pattern as before. So it's again most similar around the outside, second most similar mostly in the other direction, and third most similar mostly to the middle-sized one. And this is also true for the third group here. Again, most similar on the outside in increasing size, second most similar mostly in decreasing size, and third most similar to the middle-sized one. And to also highlight some difference, we have another group that looks a bit different, because you would expect that it also goes all around, and not that these two are a bit separated from the rest of the group. And to explain this, and to get an explanation, we look closer at the geometry of these files. And the interesting thing is, if you rotate them around, all of them have holes, because you put the cables in on the other side. And all these that are down here and form a kind of group have the holes on the opposite side of these electrical pins, which you can see here. And these two connectors don't have the holes on the back side, but on the side, which you cannot see right now. So they don't have it on the opposite side, but rotated 90 degrees, which explains why these two are a bit separated from the rest, but still recognized as similar because they have an otherwise similar shape to these connectors. And after having these successful results with these connectors, we also looked at some performance results, because the intention was to scale this up to a bigger connector database. And so we have made some performance measurements with just some primitive shapes. I think cylinder, sphere, and so on are clear. The simple connector that is described here is just some cylinders put on top on each other, so that it looks like the connector which we use for the electrical power. And as you can see here, with about 1,000 tetrahedrons, we already get about 98% volume accuracy, which means that about 1,000 connectors are pretty good to get a good approximation of the original geometry. And what we also measured is the time for the calculation of these central moments, and also file reading and calculation of center of gravity. Since both of these axes are logarithmical, this is still a linear dependence, at least until 1 million tetrahedrons. We didn't have files which had much more, so maybe at some point you will run in an issue with not enough memory, and then it will slow down. But in our case, this wasn't the case. And what you can see here, that the 1,000 tetrahedrons, which we set here, which are good enough for 98% accuracy, only take about 1 second for the calculation, which makes this again pretty fast. And with that, we come to the conclusions. Here again is the picture OSIS chain. So just for that you can remember it, we have a complex shape. We make some mesh with tetrahedrons, and then calculate central moments and dimensionless invariants. And then with distance calculation between the feature vectors, we can actually classify them. And as the theoretical results are that we have mathematically proven detection of similar objects based on the pi theorem of Buckingham, and we need no manual indexing, which eliminates the subjectivity of humans, because one human might do another indexing or classification than another. And because we only rely on the tetrahedral mesh, we can process arbitrary complex geometries. And for the implementation results, the similarity search, which is just the distance calculation of the feature vectors, can be easily done in real time. And because the time-intensive calculations, like calculation of central moments and also the meshing, have to be done only once, and then the central moments or the dimensionless invariants can be stored in a database and retrieved for distance measurements. And because this process is fully automated, it would be easily scalable to a larger connector base of, for example, 40,000, which was the case in the industrial example presented at the beginning. And with this, I finish my presentation and thank you for your attention.